So here is my ADC talk, and that's the Audio Developer Conference, and it was last year. And so the title is Spectral Audio Modeling, Why Did It Evolve, and Why Do We Need It Now, or Do We Need It Now? And as I was saying before the recording started, this is in reaction to WaveNet and others where, let me just jump to that. It's down here, DDSP, Audio and Generative AI. So here we go. So in the WaveNet paper, there's this quote, traditionally, speech recognition has largely focused on using log-Mel filter bank energies, which is a spectrum analyzer front end, or Mel frequency Kestrel coefficients. That's just the inverse Fourier transform of the log magnitude spectrum. But lately, they've been moving to raw audio. So this was kind of, in my experience, this was sort of the height of the end-to-end revolution where, you know, for neural networks, you don't need any front end. You don't need any features, all the stuff that we developed for so many decades since the mid-20th century at Bell Labs, all the music information retrieval features that people are using, you know, all the various things. Just forget it. You know, let the neural net learn what it wants to learn. That was kind of the push. And, you know, as a signal processing person, it's like, it's the experience of AI putting you out of a job, right? So who needs it, you know, when you can learn it? And so this talk is a little bit of a rebuttal to that. Well, it's a big rebuttal to that because I've got lots of hard evidence that that you do want these front ends that we know and understand. And it's especially true for any time you're working with perceptual data. So, in other words, if these are raw audio samples and you're just learning everything downstream from that, you're wasting compute. Or even if this is raw image data, you know, or telemetry from space, what you really want to do is condition it into good-sized information nuggets, and we know this well for LLMs, right? So the first stage of your neural network is to get to good tokens where, you know, the ideal token is both primitive and informative. So in other words, it's like an indivisible atom of what it is you're working with, but it's also not oversimplified. It's not, you know, it's not an atom that you would ever need to break open. And so that level is different for different perceptual modalities. And so my area is audio, so that's where I'm most concerned. And the sample is by no means a good level. You're giving up a solid order of magnitude relative to you know, good information nuggets, and you could even argue 2 orders of magnitude. And if you look at the latest audio codecs, then you see that very clearly. And I have some of that here. So that's kind of the introduction overview. That's kind of what we're going on. That's the overall arching theme of what we're talking about. Okay, so we're going to do an overview, a zoomed out overview of spectral audio modeling from evolution to AI. So we're going to cover the last 2 million years, roughly. And, but we'll skip, you know, we'll fast forward as needed. And so...
So we only have an hour. We only have an hour, okay. Julius. So we'll take
2 million years to 1 hour. That's
1 hour.
To 1 hour. Okay. So the intended audience is people like myself, you know, audio signal processing people who went to all these conferences and they're interested in what's happening in AI and how it connects and how we can contribute and all that. And it's also aimed at people in the AI world, you know, machine learning world, who want to know more signal processing, because ultimately this stuff is signal processing, especially if you're working on any kind of perceptual modality. I mean, those are signals you're starting with, right? And so in neural nets or signal processing, they started in signal processing, and they really always will be. But, you know, of course, there's been a lot of independent development in machine learning from a statistical point of view, and all kinds of pattern recognition technology. There's been a lot over the years, and I've been, you know, peripherally associated with it, watching it happen, and mostly resisted it because I didn't want my knowledge in a black box. You know, I always love to have my processing understood. I know I've got the right number of bits. I know everything is well conditioned. Everything is normalized. I know what it's doing. And if I need to make it better, I make it better, and we don't waste computing and that sort of thing. So my whole relationship with AI, let me summarize it. This is something we did talk about. It's a little bit ways down here. So this is a slide that Hyung-Won Chung had in his presentation at Stanford CS25 from OpenAI last spring. And so the conventional wisdom now in the machine learning community is that you really want to get rid of structure. So and this is particularly for frontier models. So if you have a lot of structure, then you come out with good performance early, but then you tend to plateau. And then if you reduce the structure, then you bounce along and you have trouble getting going, and then finally it gets going, and then it does better. And if you get rid of all structure and really go end to end and so on, then you'll do the absolute best. And so the very best frontier models have no constraining inductive bias structure that holds them back, and it just lets the neural network evolve anything and everything it needs to do its best. And so that's what I don't agree with, because I'm down here. I am the musical instruments guy, real-time signal processing person, and we live down here with a lot of structure, and we know what's going on, but we're impressed with these results, and so what we want to do is start with these results and then go backwards. So and of course you see this happening now. There's distillation, and there's all sorts of techniques for training smaller models. So this is a well-established area of research, and the typical paper, will keep substantially the quality level of the state-of-the-art thing and save you, an order of magnitude or even 2 orders of magnitude computation. And so you see that process, and when it's all said and done, I would really like to have, this level of performance, way back here, and I'm willing to give up some of it, and then have a lean, mean system that I understand is fully transparent, and we know it's going to work and how it's going to work. But we learned a lot from distilling the best system. In other words, you do figure out what's going on in these things sometimes, and that's very informative. So there's a back and forth that goes on that's quite nice.
So when you say you learn a lot, who's the you in that case? Are we talking about the model or the human?
I'm talking about the human. Yeah.
Okay.
And I have some examples of that in this talk here, where we learn from the neural net what's going on, and what we generally tend to do is figure out how to meet it halfway. So in other words, we see what structure it's using to achieve its results, and then and generally it's the same structure we were always using, but it's more adapted to the data and more adapted to the task.
Okay. So Dev had a question, I guess.
Yeah.
Yes. So there is this concept of meta learning, which is becoming more pervasive now with these newer models. So essentially, instead of trying to give the features to the models and for it to basically have an architecture to learn those features and then refine those and try to figure out more features. So the meta learning goes to the root data and then learns what is to be learned in terms of features, and then applies that to your model for your final outcome. So in that regard, even today's announcement, O1 talked about a lot of meta learning in terms of reasoning that it has to apply. Do you think that's akin to that? And of course, and interpretation. So the interpretability also. And again, I'm kind of mixing two topics here with O1 and what we are discussing here. But they do talk about higher and better interpretability as well within your models, which is what you're in some other ways trying to apply with the distillation or some other mechanisms.
Yeah, I think these all do point in the same direction. It's like we get the best results, we figure out what's going on in there, and then we figure out how to do the same things more efficiently. And we can either know what's going on, and so my approach is to recognize structure and then give it the same structure, but in a way that is more parameterized. And I'll show examples of that. so that it can train more efficiently on this structure that is now adaptable, but also constrained to be in the right structure from the beginning. And then the other way of doing it is you just distill without knowing what's going on. It's just, give me a smaller model that gives the same logic distribution, and I'll be happy. So it's just pure data reduction, complexity reduction. And I missed the first one you mentioned. I missed some of the audio.
Yeah, I'm sorry. Something is wrong with my AirPods that I need to figure out. But that's okay. I mean, we can. You please continue. I'll bring that up later as it makes sense.
Perfect. Okay. Anytime. Okay. So this is the setting. And so it's signal processing talking to machine learning and vice versa, and it's a very fruitful dialogue. So for this audio situation, I wanted to start with, if end to end is so great, why aren't our ears just little pinholes? Why don't we just have a tympanic membrane right there on our temples that goes straight into the auditory nerve? Right? I mean, what's all this hardware, right? That's very specialized. Doesn't that restrict the ultimate hearing solution? And so I want to, maybe review that a little bit and give us some insight into that. And also, it's interesting to think about how that evolution of spectrum analyzer hardware in the ear drove our need for spectrum analysis and processing and all kinds of related topics. It just kind of followed from that. In some sense, it just sort of committed us to a particular road that we're now on. And so...
hey, Julius?
Yeah.
Yeah. Monica had a question in the chat.
Let me look at the chat.
So the question is, what does structure really mean? It could be raw audio, music, or something else more deep, like pitch.
The structure I'm talking about is mostly the neural network computations. And let me just jump to one of them. Let's see, where's the good one I want to show? I really like this one. Well, this is a good one too. But this is the one I was thinking about. All right, so this is an F0 estimation task, okay? That's pitch detection. And so you can see that, a raw waveform comes in, just like in WaveNet. They typically use 8-bit mu law. And it's just, standard deep learning sorts of, just an MLP kind of thing. And this was done at Stanford. I worked with Pratik Verma, and Ron Schaefer is at Stanford teaching, and they worked together on this. And I learned about it just talking to Pratik. So what they were doing is finding the pitch, and so they thought, well, maybe there's an auditory filter bank in the front. Let me just tell you, the usual thing we would normally do. Let's say this is signal. Then over here you would have an FFT and or the DFT. It's a matrix multiply, right? So this is a matrix multiply. That's all it's showing you. So you have a signal coming in and you multiply by matrix. And for us in signal processing, this would be a spectrum. So you go from signals to spectrum in one layer, and then. And of course, it has activations, and what we would normally then have next is a peak detector. So this layer would just be doing something like the optimum comb method of peak detection. So you're basically looking for harmonic support of fundamentals, and then and whatever fundamental frequency has the most harmonic support, that is your pitch, right? And so now you need a layer to then, find the max of this layer and put it out. I guess really there's one extra layer than you need because this could do that, right? So I was also thinking about the chord estimation problem, and that would get you up to 4 layers because you have to have a signal, a spectrum, the peaks, and then chord detection, and then you can put out, what's the most likely chord. So so this just ordinary signal processing tends to look like this. And so the hypothesis was maybe it's doing that, right? Because optimal signal processing is optimal. You can't change that. And so is it doing optimal signal processing or is it doing something else? And so so the first thing to look at is does it do an auditory filter bank on the front end, which is it's like an FFT, but it's more adapted to perception. So your low frequency channels are more narrow. So it's like a narrow band filter bank at low frequencies. And as you go up in frequency, it gets wider band. And that's the way the ear evolved. That's what the ear does. And so so they looked for that. And the way they look for it is each neuron is, if you're hypothesizing that it's a spectral node, you just take all the weights leading to that neuron, and that would be your windowed sinusoid, and then you just FFT that, and that is the frequency response of that filter band, and that's what these are. So let's say this neuron is over here. This neuron is over here. There's obviously many more neurons than we have in this picture. So each slice of this, each vertical slice of this, is the FFT of one of the sets of weights leading to that neuron. Okay. And so it's filter frequency response. And so they had to be sorted, right? They don't come out sorted. And so you sort them by peak frequency and plot them like this. And you see that the center frequencies have a lot of coverage over the range of fundamental frequencies in the data. And then they go off like an ordinary auditory filter bank. So you can see how it's adapted to the task and adapted to the data. And so it's a distorted auditory filter bank, but distorted in a good direction for the problem and for the data, for the range of ages in the data that give you a particular range of fundamental frequencies. And so that's just a beautiful example. So what it immediately suggests is that you want to now tee it up with a filter bank that is differentiable, so that it can train, so that it can optimize it, and let it achieve this without doing it the hard way, because every single sample along these spectral slices is an independently evolving, the gradient descent has to optimize each and every weight, and that's just a lot of optimization and degrees of freedom that you don't need, right? The degrees of freedom you evidently really need in this situation are the center frequency of the band and perhaps its bandwidth. You can see that these are wider band up here, and that is normal. So the higher frequency bands are wider band. So that's what we're doing. I'm working with some students right now to do stuff like that, where we're basically we're replacing like this layer, or just giving it a first layer that is known signal processing that we normally do, but opening up the parameters to make them trainable, so that the optimization, the gradient descent, can tune it to the data and to the task in the same way that this end-to-end system is. And so we're expecting orders and orders of magnitude of more efficiency and more interpretability. When it's all said and done, we know exactly what's going on. And another basic principle is you can do this in a mixture of experts kind of way, so that at the same time you're doing that, you can have this, right? And so you can just think of it as there's sort of the prescribed structure layer, and it's like a different expert. And then you have this routing layer just above that decides, do you want the tunable known structure, or do you want the completely freeform unknown structure, given that the solution here is structured? And I think we'll be able to prove that the router is going to like that. And I think the only real risk is it as convex? In other words, the properties of optimization are critical, right? And so these are known to be very optimizable. These weights, at this neuron, the error is linear in the parameters. These weights, it's kind of the easiest optimization in the world to minimize a linear combination. But of course, the activation throws a a monkey wrench into the whole situation, and it was fatal until they made them soft, right? So in the original perceptron, it was a step function, which is not differentiable. The gradient tells you the gradient is zero everywhere, but infinity at the step, right? And so, and someone had the brilliant idea. I don't even know who it was to make it a soft. I think it was like arctan, TANH kinds of things at first, and then progress through all the SWILU and GUILU, all the things we have now. But it needs to be something soft that the gradient can get through. And that was the big breakthrough. That was the big backpropagation breakthrough to make the whole thing trainable. And apparently it doesn't destroy convexity too bad. I mean, I think it's known that up to 2 layers, it is still convex optimization, but then they lose that. But it's obviously not too far away because we're training these giant networks. But with skip connections, I just expect some theorem to come along that says, if you've got a skip connection, then you've got a convex optimization problem, and some big theory result. I bet it's going to result, because these things are so trainable. But they also do get stuck. So if they get stuck, then you have a proof that it's not convex, but they're so substantially convex. And so when we're putting in known structure, that's the thing we have to worry about is, are we making this untrainable or not, or is it still trainable? And so we have to really think about what our prescribed structure, what the form of it is, so that it's differentiable and it can easily get where it needs to go in a gradient descent context. So that's what I mean by structure.
Yeah, Dev had his hand up. Dev, or do you want to?
Yes, I don't know if you can hear me better now, but I'll try.
Yeah, we can hear you.
Okay. So 2 questions. So one is, how transferable is this mapping from this waveform analysis to, let's say, any other kind of time series waveform, let's say EEG data or any of that data? That's question 1. And then taking it to the next level, where what are your thoughts in terms of anomaly detections in that context? So I don't know if it's relatable, but those are 2 questions that came to my mind when I was looking at this.
Well, I have a good answer for the first part, but what do you mean by an anomaly?
Well, one of the big things in terms of EEG analysis is to find out whether it is anomalous or good. So so that's what I mean by that.
I see. So you want to know, is this a normal EEG or something weird about it? Is that it? In other words, looking for anything out of distribution of normal and healthy.
That's correct. And the other thing was the periodicity, like the EEG data is periodic in nature, again, versus this data, which may or may not be periodic.
I did not catch that because of noise, both here and on the other side. Can you just rephrase it, maybe?
Periodic. It's repeating, periodic. Right? Yeah, periodic.
Yeah. Well, let me show you my my answer on the first part, and then we'll talk about the other one. So let's go to origins. So this is the answer for hearing. Okay, and in other words, in the case of EEGs, I would want to know what exactly they mean physiologically, and I don't even, maybe we don't even know that, but if it's a perceptual modality, then we know a lot, right? So this is what we know about hearing, but and we also know a lot about vision. We know a lot about tactile touch. So for the normal perceptual modalities, we have a ton of information about what the prescribed structure should be like, because evolution has told us, right? This is what was adaptive for us, and that's a lot of structure, and I guess it's just a system of constraints. So this would be the end to end, right? So in other words, you should just be able to cut all this away if end to end is right, and just have a membrane here that transduces into this auditory nerve. And why would you need all this signal processing garbage going on in here? Well, it turns out we need it because these nerves have limited frequency response. A neuron is kind of living on the order of a millisecond firing and recovery rate, and so it can't really track anything more than 500-600 hertz. Kilohertz is just too much, right? And so if you want high frequency hearing, then you need some trick, right, to get these 1 millisecond neurons to be sensitive to be able to do spectrum analysis out to 20 kilohertz or even 10 kilohertz. And so that's what this hardware gives you. So each individual neuron is still, very limited, but its place, its location along the spectrum analyzer is frequency coded. And so you do get the information. It all goes in. Here, that's the balance system here. And then these bones are doing an impedance match. They give you a lot more gain sensitivity. So to be able to handle really, really quiet sounds, you need this because you're going from air into a liquid. So this is liquid over here. And vibrations in air do not transduce efficiently into liquid. And so this is a little impedance matching bones configuration that helps solve that problem. So you get a huge sensitivity gain, and here you get a huge bandwidth gain, and so you expand our sensory capabilities. But you could say, well, it's all based on just being in the real world, and if we don't have that problem, if we have a microphone and an A to D converter with plenty of clock rate, then maybe we should be able to do an end-to-end system, and that's true. But it's not going to be human, right? And I have a talk about that as well, a little example for that as well. Let me I saw it just a minute ago. I'm trying to find this. Yeah. So this is Josh McDermott's perceptual modeling of hearing. And so there's this neural net, and it's deep learning in its nature. And so what they found is that they really do need this ear. So this is a cochleogram, which essentially models all that hearing hardware. So it's got the sort of time frequency distribution of energy that you get coming out of the ear into the brain down the auditory nerve. And so you could think of it as an ear simulator. It stands in for all that hardware. And then it goes neural. And then you have a division between two different tasks, word classification and genre classification. And so, yeah.
By genre, do you mean music genre?
What was the full sentence that I said?
Yeah. By genre, do you mean music genre? Like, country western versus rock and roll?
Or? Here, I think... Let's see what it says. Yeah, music genre. Yeah, so this was John.
Oh, it is. I'm sorry. I should have just looked over there.
Yeah, and I it's been over a year since I read this paper myself. So
yeah, that's okay. I should have just looked at that. I apologize for interrupting you.
Well, I probably had it like that. So I just think this is a great argument for why we keep the ear simulation because it's real results. So they really did this in the lab. So first of all, they settled on a 12-layer network as the best for word recognition and music genre classification. They tried 180 cases, and they also found that they could share the first 7 layers, which is really nice. So there's this like common processing. It's like a little foundation model for audio, tasks, and you could have a little fine tuning or just a little secondary network for classification of word or genre. And so what's really cool is that it performs at the human level and it has similar errors. So when it gets it wrong, it's when a human is more likely to get it wrong. And that is directly a result of this auditory front end, just having human hardware simulation at the very front end. And one of the amazing things they found is that they were able to predict the fMRI responses in the audio cortex.
So to net that out, does that mean if I'd be able to classify what the sound was or what caused the sound to occur? Is that what you're saying by that fMR response? I'm sorry.
I don't know what they're predicting. In that case, I would have to reread the paper.
Oh, okay.
I have
No, that's okay. It's okay. Don't. It's
Yeah. I don't remember exactly what they predicted. In other words,
I'm just finding this very fascinating that, somebody essentially built a neural network to match all these structures in our head,
Right.
And to get the same level of performance, shall we say.
Exactly. And the
fMRI would be kind of what parts of the brains are activated by the audio signal, right?
Yeah, but high up, right? So
it's a functional MRI. So it's focus on the function.
So you're really talking about taking somebody's head and jamming it in a machine and watching and sees what lights up, right?
Magnetic resonance imaging.
But functional, so that it's in real time. So you have a live human sitting there listening to audio, and you're watching the MRI in real time with some delay, but not bad. I think it's I think it's a lot like that previous case I showed you, where they have a firing pattern, and they basically found, they searched over all possible sorting of their firing pattern to get it to match up, to get it to line up. So they were able to do that. They were able to align the virtual audio cortex with the real audio cortex with some, reshuffling permutation and finding the right layer. So here's an important point. You needed this cochleogram if you wanted to predict human responses. So, and they did try, and he didn't say, I don't remember this in the paper, but Josh McDermott gave a talk at Karma, and he said in his talk that they tried getting rid of this cochleogram, and it was possible to do better than human on various tasks, but the errors that it made were much more alien. In other words, it evolved hearing that was very different from ours, and so it was not nearly as interpretable, or would not match up. So if you wanted to be human in its, both successes and failures, then you need this. You need this sort of hardware front end that evolution committed to, millions of years ago. So it's a question, how human do you want it to be? And if you don't care about the fact that it needs to be human in any sense, then go ahead and get rid of it and see what trains up, and just adapt purely to the task, purely to the data. And we have that in my area too, where sometimes you need human responses. Sometimes you just want the best answer, like I want to know what the frequencies of the piano string are, and I don't care, I want superhuman resolution here. So those are two fundamental cases, but the human-oriented case comes up a lot, and in those cases, then we still need this. And you could still argue that, well, this would evolve, right? So if you set up your loss function to demand that all the failures be human-like and so on, then theoretically this would evolve. Maybe not in the front layer. Maybe it's distributed all over the place, but somewhere it's just got to do it, because that's the sort of constraint space. That's the manifold that it lives on, and you're just going to train much longer, and you're going to need a lot more data. So the thing is, if you know you're going to be simulating a human perception, then you get a huge advantage from providing the perceptual front end as a given. Make it adaptable to the extent that it's reasonable. We have various mechanisms for adapting to sounds, automatic gain and things like that. So you're going to say you don't want to evolve an ear necessarily. That's just a lot more work. So that I like. That was a good demonstration. That was the one right before this.
Yeah, that's pretty fascinating, actually. I don't know about anybody else, but I found that pretty fascinating.
Here's the author, Kell et al. It's published in Neuron 2018, so you can pull this paper. And what I would do is just go to search for Josh McDermott, MIT, and just get all the latest papers and get the latest results that way.
Okay.
I'm not sure if I understand it right. So, because I found that the MRI detects it's treating human brain as like a magnetic sensor, and it's basically used to detect the signals from the human brain, basically like how human brain understand the words. Is that correct?
I'm sorry, can you repeat? I didn't
So
quite.
MRI is can I understand MRI as something that like it treats human brain as a magnetic stuff. So it's kind of like sending out. The human brain is gonna send out signals if it is like thinking something or understand something. Is that correct? So if we
Yeah.
if we have a kind of like a sentence as insert, we can use this technique with neural network to predict how human brain will react to the input audio. Is that like what research about?
I think that is one of the things they are really looking at. Yeah, I think they want to try to predict what happens in the brain. And one of the big applications of that is, novel hearing aids. For example, what sort of transformation? Let's suppose you train up some sort of hearing assistance here, and there are products like that now on the market. Phonak just announced one that's really cool. It's got a big chip, the biggest chip that's ever been in a hearing aid. And it does give you a very sophisticated neural network for noise reduction and hearing enhancement. And so if you're trying to come up with that, a reasonable question is, what transformations will help? So if you can take the standard spectrogram and do some transformation on it, does it make you hear better or not? And if you have a proxy system so that you don't need to bother with human subjects, you just go ahead, you've got this human proxy simulator, then you can see, well, do I hear words better or not in my virtual system? And if you do, then you can ask humans, well, does it help you as well? So there's a lot of applications in improving things for humans by just having a virtual version of it. And so the MRI test is just one way to verify that, yeah, we're simulating the processing very, very much like a human. We can map our neurons to their neurons in the higher order cortex. And the higher levels of the audio cortex are very very quiet. They're very. I think it's S4. One of the papers I read said most of the neurons are quiet most of the time. So you're listening to audio, and there's just there's a very sparse set of activations as you listen to audio at the fourth layer. So we'd like to find what those are, and it's taking hearing modeling out to higher layers and trying to stay synchronized to human processing as much as possible, because then we can help humans with this processing.
Okay, thank you.
Yeah, that's a good one.
Dev, you had a question?
Yes, I posted it on chat because my audio is troublesome.
Let me look.
Okay.
And part of the problem is I need one of these systems. I need this pre-transformation myself. I'm not wearing any kind of assistance, but I guess I can crank up my audio. It probably helps if I crank it up. That's the usual rock and roll solution. Let's see. Do you think Apple AirPods hearing aid use anything? I bet it does, because they've got the neural chip, but they have to do it all in the EarPod if it's going to be instant. But there could be a lot of dialogue back and forth. Does anybody know what's in the new AirPods 4 that just got announced? I have AirPods 2, and they're great for noise cancellation, and they're really quite good. But I don't know what's in the 4. Oh, and also the AirPods 2 will get this new hearing aid feature as a software update. So I guess that just means it's an EQ that's customized. So they have a hearing test, and you go through the hearing test, and then it just gives you the right boosts. Mostly hearing aids are just compressive gain adjustment. So you want to find the hearing threshold across the frequency band, and then for older people like me, it's there's a threshold elevation. There's actually an ISO standard on this curve, and it happens to everybody. Happens to men worse than women. So what it does is elevate your threshold. So this is low frequency, this is high frequency, and can you see me actually? Am I actually projected, or is it just? Okay.
You're showing in the little window on the side.
The thumbnail? Yeah. Okay.
Yeah.
Because I got to do my graphics in the thumbnail here. So as the threshold goes up, you've got some ceiling here, which is like a clipping threshold, right? And so when your threshold goes up, you can increase the gain so that at threshold you hear things like a 20-year-old, but then you can't go all the way up. It'll actually hurt your ears if you don't compress. So you compress the normal dynamic range into your remaining dynamic range, and so your threshold is normalized, and your peak amplitude is normalized, but you lose sort of difference Lyman's, they call them, just noticeable amplitude steps in between. So you can't tell exactly how loud things are, but that's the basic theory of all these hearing aids. And so it's not hard, right? It's just multi-band compression, but you have to know your threshold, so you have to do your hearing test to get that, and then it's just a plain equalizer to elevate to your threshold, but then you need that compression to normalize the upper level. And I had one audiologist tell me that you actually want to not go all the way to the maximum, that you want to kind of bring it down. But that's kind of a second order effect. I don't find that I need that. I wrote my own app for doing this, and it works just as well as my hearing aids. So I guess that is what they're doing. But now that we have neural networks everywhere, you can get things like the cocktail party problem solved, where you're in a noisy restaurant and it really does strip out everything but the person you're looking at. And that's going to be great, right? To be able to go into a very loud party and talk to one person, that's a huge thing.
Well, maybe the AirPod 5 or AirPod 5 or 6 will have that capability that you can, focus isolate or whatever you call.
Yeah, you need a pretty good amount of processing in the actual earpiece, right? Mm-hmm. So the Phonak unit is bigger than their normal. So it's a large unit. It does fit behind your ear, but just barely. Mm. And so the AirPods, I don't know, they've got a reasonable amount of volume inside of them. Mm-hmm. They might be able to fit a reasonable sized chip in there.
And they've got more money than God, so they can, if they need to go to a new technique, Apple probably, if they had the will, they have the way,
Yeah.
Julius,
yeah.
They don't really need to be in here. They just need to have a low latency connection to something to do the processing, right?
You're talking about latency. There was a lot of echo in what you just said.
Oh, sorry. Why don't you go on? I'll see if I can correct that here.
Did anybody get it? If somebody with better ears just sort of replays it for me, I'll be okay.
How about now? Can you hear that?
Mm-hmm. That sounds good.
Okay. So what I was saying is that to have these advanced hearing aids, you don't have to push all that computation into the AirPod. You just need a high enough bandwidth, low enough latency connection to something on body that could do the processing, right? So I carry it around in my pocket or whatever.
That's a good point. Yeah, as long as they're not Bluetooth. Bluetooth is no good, but a Wi-Fi connection, some kind of custom. Yeah,
custom RF.
Yeah, just insist that your phone be right there with you. And what did you say besides Wi-Fi? So yeah, all I know
just
is
any sort of RF connection.
Yeah, any kind of
designed for that.
Absolutely. Right. Yeah, they could just have their own transmitter receiver system. They could bypass Wi-Fi and Bluetooth and everything. Yeah, that works for sure.
The other angle on that is you can also tie in the image, the video portion. I've seen neural nets that do lip reading.
Wow.
Yeah. They could also contribute to that.
So that would really work for the noisy dinner. You're at a restaurant that's just noisy as all get out, and then it's obvious who you're looking at, right? So
exactly.
Yeah, so it's got your. I guess you're wearing the glasses and looking around, and your hearing aid just kind of gives you a nonlinear focused beam.
Yep.
Yeah.
Looking forward to that.
Let's write a patent on that, guys, first, and we'll sell it to Apple.
That's a crowded area. I have friends in the hearing aid industry, and boy, they have so many patents.
Oh.
And this basic idea has been addressed. Audiologic did it, and I'm sure others. And they were doing it with FFT processing. So you would basically take a stereo recording and strip away everything from the wrong direction. So each FFT bin would get squelched based on look direction. And it worked, but it was kind of artifacty. You could hear, the brain doesn't like artificial processing. It's just kind of this crunching noise down at the low levels, which is distracting. I imagine you can get used to it, but you can also get used to interference. And so it's hard to beat the brain as a optimal signals and noise processor. And that's why most hearing aids just try to give you the ideal level across the frequency band so that your brain can take it from there. It's just well known in the hearing aid industry that the brain is your best signal processor, but these neural nets, I think, have taken it to the next level to the point that that's no longer true. I think the fact that Phonak came out with a product seems like proof enough to me. So I'm looking forward to it.
Yeah,
Julius, another question: the cochlear model that you have on the front end. My understanding is that the geometry of the ear, like the external structure, helps with some sort of directional detection. So not talking about the cochlear, but actually the ear, the fleshy out. Yeah, Is that?
That's right.
Have you heard of that?
Mm-hmm. Let me find my picture of the ear. I guess I should go into Origins here and go. Here it is. Let me full screen this, and this is my history of evolution. Right. So where does elevation perception come from? And it's from this weird shape. That's why our ears are so bizarre shaped on the outer ear. And so when something comes in at some vertical elevation angle, you get a differential excitation of this cavity and everything else. So this is evolved to give you basically a notch. And when I looked at this stuff, the notch was roughly somewhere between 5 kilohertz and 10 kilohertz, and the elevation angle would move that notch around. And there's some other things, but to first order, that was the most prominent feature that you could see in the spectrum. And then your brain evolves to recognize that notch as an elevation cue, and that's why HRTFs have to be ideally using measured ears, and they're doing it with pictures. You can take a picture of your ear, but for a long time there was just a very generic ear called Listener M, and that was a pretty good proxy for everyone, and most people would hear pretty well with that, hear elevation. So it's ideally your ears that give the HRTF elevation, but in most systems you don't get that. But
Julian, what is HRTF?
That stands for head related transfer function.
So it's a geometry, your ear geometry type thing?
The ear geometry determines the head related transfer function. So if you get rid of the outer ear, then you just have the transfer function of a pinhole, more or less, because the ear canal is smaller than the typical wavelengths of audio. Audio wavelengths, it's about a foot per millisecond for the speed of sound, 1.1 feet, I guess. And so if you have 10 kilohertz is going to be, like a tenth of a foot. So you can see that the cross section of the auditory ear canal, the outer ear, is below a wavelength over almost the entire audio range. So this is kind of a pinhole sampler of audio, and so that doesn't have any structure in it. But if you put this outer ear out here, then you can get a geometric filtering that introduces a notch. It's kind of a multi-path notch that then just is in the sound as it comes in, and that gets transduced and processed by the brain, and you get elevation perception.
Wow, this is some elegant engineering.
It is, and it evolved, right?
But
I really like this figure because it talks about the evolution of hearing in the ocean, until here. Right? So you can see that it started way back here. I guess jellyfish can hear a little bit, and then the mollusks and arthropods. They all independently evolved their own hearing systems. But what's really interesting to me is how similar they are in many ways. They seem to have a very similar vestibular idea. Their solution for balance and orientation. It's really a fascinating topic. But it's hardware, right? So evolution said you're better off with a committed signal processing front end. That's what evolution says.
Huh.
So we still have to be able to simulate.
Julius,
What?
you said that these were independently evolved. Is that
after
using genetic mapping, or?
I'm just saying, after they divide. I mean, once you have the species division, after they're separate species, then that's independent after that. Although, similar environments, so they're competing with each other, they're eating each other and all that. But and anatomically, they're genetically separated. So it's a fascinating hardware evolution. And this is in case anyone doesn't know, this is how the ear does spectrum analysis.
So wait, different frequencies or different parts of the. What is that? An ear the inner ear canal, right?
Right. So it's this snail thing, the cochlea unrolled somewhat. So the input comes in here from the bones of the middle ear, and the high frequencies come first, and that's where the basilar membrane is extra thick and stiff. So it resonates at a higher frequency. And so then as you go farther in, so you basically have a traveling wave. So your audio sets up as a traveling wave going down the basilar membrane. And you can think of it as a superposition of different frequency components. And the high frequency components resonate near the entrance. And so that's where your high frequency perception comes from, is just this high frequency resonance at the doorway. And then as you get farther down, 5 kilohertz resonates here. And so as the as the wave packet progresses, the higher frequencies are stripped out, and you have only the lower frequencies left until you get all the way down to the apex, where you've got roughly 200 hertz, it looks like, but it's even lower. I don't know, maybe you experience 40 hertz in a different way. I don't know. I think this goes down to 40, but they only labeled it down to 200. So this is your basic hardware spectrum analyzer. And then there are nerve cells all along the outside that the hair cells, they call them, that then feel those vibrations. So when you get the resonance, the nerve cells at that frequency area resonate and send a frequency encoded firing into the auditory nerves. So the different auditory nerves have different frequency mappings. And that's how we get our high frequency perception.
Huh.
So this is a hardware spectrum analyzer.
How does hearing loss with age occur at that level?
Well, can I just add one thing to kind of a question as well as comment before Julius answers that?
Sure.
So a specific frequency, once I had some rats and mice problem in the house, and they had some videos to play really high frequency, high pitch frequency sound. And I couldn't hear it. They said, those animals can hear it. But my children could hear it. So, yeah. I mean, by my age, or even before that, in 20s, we lost a lot of high frequency detection.
There is a device, and I'm trying to remember what it's called. It's available in England, and they put it outside of like where kids congregate. They don't want them to congregate, and it plays a frequency at a higher frequency. And I guess after about 18 or so, you lose your ability to hear up in that level. But it sounds like a buzzing mosquito, I guess, is the net of it. And I'm trying to remember. I don't remember what the name of the device was. It was really fascinating, though, that somebody built this thing, some engineer, specifically to drive away teens so they wouldn't hang out in front of your store or whatever.
That sounds useful.
Yeah. And apparently it sounds like a really loud mosquito, on your ear or face or something like that. So very negative reinforcement.
There's also the hearing spotlight, the audio spotlight, where they can aim a loud noise only to you. And you can actually have a private conversation with somebody all the way across the room using. So it's a very high frequency, way above human hearing. But once it hits your ear, it gets down modulated by nonlinear interaction. And so you hear the demodulated audio. Audio Spotlight, I think, was the name of it. I was looking for the standard hearing curve, the standard loss. So this is an example of impaired and normal, but even the normal is rolling off. But yet there's an actual ISO standard that talks about what the average hearing loss is as a function of age for men and women, and it's very, very typical, and it's just normal. And the way I think of it is, we just wear out the neurons at the entrance to the basilar membrane. They just get too much traffic. It's like an old, doormat that's just had too much traffic, and they're just worn out over time. But the low frequency lasts much longer.
So that device is called the Mosquito. It's audible only to teenagers, it says. So, if you don't want kids hanging out at your 7-Eleven, there you go.
Oh, it's so cool to teenagers.
Yeah. It won't work for most of us, though. We're just too damn old.
Well, there's a fix for everything.
Yeah. Anyway.
AI to come along and clean all this up, right? So,
yeah.
We'll eventually have cellular regeneration, and we'll turn off all of our cells will revert to being, age 25, and the DNA is still there, right? It's like the information is still there. So,
yeah, but it's probably like me. I can't remember what I had for breakfast.
Well, that'll all come back, right?
Maybe.
Yeah.
So we are at time. We are pretty much at time.
Oh, okay, nice. Yeah. Well, let me just kind of give the finale here. So my sort of rhetorical question is: will spectral modeling continue? And the answer is, I think yes, because ultimately, if no other reason than to just be efficient. So I have here. This is what I was looking for. So we can see that our brain, we have evolved hardware in our ears to extend our frequency response and sensitivity, and the time frequency distributions are fundamental to human audio music perception and appreciation. And so if we want to keep that, we're going to need to keep these front ends. And so, there's some points I didn't get to, but they're pretty obvious. So here's the basic bottom line. AI can reinvent spectral processing, or we can provide it and save it a lot of training effort and a lot less data, a lot less training. Neural concatenative synthesis is what I would say is happening now in things like Suno and Udio, assuming they're using the state-of-the-art papers in this area on like Music LM, Music Gen. They're all using basic variations of SoundStream. I don't know if you've heard of SoundStream, but then also encodec and then Descript. So there's a series of codecs, and they're all doing what I would call neural concatenative synthesis. So it's time domain corpuscles of energy, and so that's just inefficient. And I have some slides to argue against that being the best way to go. And so Another place that we're still using spectral methods is in loss functions, so adversarial losses in particular, and also reconstruction loss. So again, you could evolve this. The GAN discriminator could just evolve, from scratch. But we know what the right answer is. We know what the distribution. We can impose our distribution a priori with an auditory transformation. We know what the in distribution sound space looks like. We've got enough information on that. So why force the neural net to learn that the hard way in a GAN kind of configuration? That doesn't make sense. It's just a waste, right? And so then this is something that I've talked about a little bit before. This is that idea of differentiable structure that we can then adapt along with the neural network weights. It's just basically adding more structure. So neural networks have a very simple structure that's repeated on a massive scale. Maybe we can add some more targeted structure that's just as trainable, that will be orders of magnitude less work to train, orders of magnitude less data and training time. So that's the sort of goal, and so that was my takeaway. Although I might be a little biased, but I think I have a pretty strong case. So that's that. Right.
Well, that was fascinating.
Thank you.
Yeah,
it was fun.
I don't know about what anybody else thought. I thought it was really, really well done.
Well, I tried to emphasize the AI or the machine learning more, which seems right for this. For the audio developer conference, I was, they're more rooted in audio signal processing, so tried to tilt it in this direction better.
You did a good job. You haven't lost your lecturing skills, my friend.
Thank you. Well, thanks. Well, it helps to have interaction. It helps a lot to get questions along the way, so I get a feeling for where people are coming from and what's interesting and how do we frame it together. Finding that common ground of framing.
Yeah. Well, speaking of questions, does anybody have anything else for Julius? Okay, we'll let him go. All righty. Well,
Thanks
I'm going to stop.
Yeah.